picture of laminar flow versus turbulent flow. So just you probably will have some relation to it. Actually, we're going to look at turbulence next time, I guess. It's the last thing we'll do in scaling. So now I think I'll see if I can navigate to. Aha. Learning by doing. Okay, and yeah. Let's look at this swinging pendulum. And we'll use dimensional analysis to see that our original assumption was wrong about things. So we have the following situation. We have a roof here, vertical direction. We have a pendulum with a mass. Let's call it big N, so we don't take it for meter, which is a small n here. Let's call this length L. We have an initial angle from equilibrium position, alpha naught. And we have, of course, gravity that drives everything, acting this way. This is actually quite a difficult problem to do exactly. It's a highly non-linear differential equation for the position of the pendulum as a function of time, but we won't do that. We will assume that there is a relation again between the frequency, that's the one we find, not any function, the initial position, the length of this pendulum, the mass, and which planet we are on, the acceleration of gravity. The pendulum would probably behave differently on Mars. Okay, so this is like G alpha naught, this is the frequency. So let's make the dimensional matrix for it, dimension matrix for this. So we have, okay, so let's have meters. Let's use, we could either write dimensions here, like mass, length, time, but if you just stick to using the units we are used to, we use the SI units. So this is meters, seconds, kilos. We have the frequency, initial angle, length, mass, and the acceleration of gravity. Okay, frequency is per second, number per second, so we have, that's the one that goes in here. And then we have this initial angle, which is dimensionless, so it has zeros all over. Mass is, of course, mass. And G is meter per second squared. Like that. So now we see quite easily that, say, these three vectors are linearly independent. Did I forget something here? Yeah, and it's a bit crammed down there, so yeah, by the way, I was messing a little up here. So, but the idea should be clear that the remaining row vectors is a linear combination of the basis vectors. And these numbers that appear here for each of the non-core variables are the ones that are here. So the idea should be simple. I think I have it correct in my notes. So But when you're being so general, it's easy to, with these double indexes, it's easy to, yes, sir. Should have practiced a little more. So this is the list of the core variables, or the basis, and this is the list of the indexes of the non-core variables. Okay, so let's try it again. I think it's fast. Omega, alpha naught, L, and so obviously, we have three linearly independent vectors here. So we can choose three of these variables. Now, alpha naught is dimensionless, so that's already dimensionless, so we don't consider that one. So we can choose, for instance, the first one, the third one, and we see we need to have mass also as a core variable because the row space is three-dimensional. So why not have, yeah, let's have L, M, and G as core variables. So if I want to make dimensionless numbers now, we need this omega. So how do we, if you see here that if I take L divided by G, that's usually the way I do this stuff, L divided by G. L divided by G, that is what dimension does that have? That's second squared. And so if I take L divided by G times omega squared, I get unit 1. So that means that we can write that. Yeah, and that's all. So our original relation translates to, yeah, we need this one, and then we have L G omega squared and L M G. So that's expressing stuff in new variables. And of course, these are dimensionally independent. So it translates to, yeah, let's call this pi 1. You could also use the square root of this if you like, whatever. So in this way we could solve for omega and get the frequency as a function of alpha naught, L and G. So we see that the mass is not included. So is it possible to, so the original assumption that this depends on mass as well is not valid, because we are disregarding air resistance here. And none of the other variables include mass. So is it possible to get rid of this mass to make a dimensionless number? This would correspond to the following situation if we translate this to linear algebra. Following picture, if I have a plane here, I have 3 vectors in this plane. Let's call it A1, A2, A3, and we have a 4th vector that's not in the plane. And since these 4 vectors, the span of them is a 3-dimensional space, we have 3 core variables, so 3 basis vectors for this span of these vectors. And we see that A4 always needs to be in such a basis, since the rest of them lie in the plane. And the way we make dimensionless numbers is to write non-core vectors, to call it that, as a linear combination of the core vectors. So we see we have to pick 2 of these 3 vectors in that basis and express the third one in terms of these 2. And we see that A4 is never involved in this expression because it's not in the plane. That's why the variable corresponding to A4 is not included in the equation. So that's how we can derive that a relation like this must be independent of the variable corresponding to A4. So it's nice to have these pictures to try to understand a bit what we're doing in dimensional analysis. Really. Okay. So how far have we got now? I think we are more or less finished now with that. Yes. Okay, so let's go over to the next topic, which is scaling, which is very related to dimensional analysis. But the difference now is that we are more specific about our problem. Instead of just starting, we have a relation between blah, blah, blah. We usually start with a differential equation. And we analyze that differential equation and find appropriate scales for the different variables. And then we write our equation in so-called dimensionless form. That's the idea, to a sense. Doing this has several advantages. So let's have a heading here. Okay, scaling. We have a problem at hand. Usually, a differential equation or a system of differential equations that's usually the starting point. Not always, because we can also use it for other stuff. And then we try to find representative scales for the various variables. For instance, if you have a stick or a rod that has length L, the appropriate length scale would be the length of this stick, to put it that way, for instance. This has, and then, well, and then write the equations on so-called dimensionless form. This has several advantages. One, our dimensionless variables. Now we typically look at, we are looking at the differential equation, so we have something that changes with time and space, for instance, or of order 1. I haven't really defined what order is, that means they are. It could be that, like if you have a length scale L or something, when and we say that, okay, so let's choose L as the basic unit for length. Then our dimensionless number, x, will go between 0 and 1. So it's kind of the percentage of the whole stick. We'll see this. Also the time, typically we scale time so that we choose a new time scale. So time after one dimensionless time, typically things have happened. Significantly change in the system. So they're kind of representative. 2, we get rid of a lot of, physical constants. 3, that's important too, because we get often very clean equations, not very many constants usually, and it's much easier to do the math with it. We don't have all these constants we have to drag along all the time. That's really nice. 3, it makes us able to see what terms are small in the equation. In a proper manner. I mean, if you have a differential equation, say a second order differential equation, and the term in front of the derivative, for instance, I mean the coefficient for the term including the derivative, say, is a small number when expressed in physical units. It doesn't necessarily have to be small really. But when we have scaled the equations, we really can know what is small, perhaps, and what is big. So these are the things. So the idea is to introduce dimensionless variables. It's also nice for numerics, because in numerics you discretize your equation, but if you do it directly on the equation, really something that seems to be small here is really big there or whatever. But when we have it dimensionless, we are kind of much better suited to know that the numerics will do the right thing for us too. By I would have written this. Appropriate scales. For instance, as I said, if we have a rod or a stick, perhaps you want to see the temperature. We'll do this example right now. We choose L as length scale. EF. And now I'll show you some notation. That's a bit awkward notation. Usually I don't use it myself, but to be clear here, we'll use it. So we say that the physical length is x with a star here. So that's in meters, say. And if the stick is 20 meters long, L, we write this x star as L times a dimensionless number x, which then will vary between 0 and 1. Typical, so this is the physical variable, and this is the dimensionless. So that's the notational thing. Often it's not straightforward to find appropriate scales for stuff. There might be, some are quite obvious, like if you have a situation where we're studying something in one-dimensional stuff on the SS length L, then it's quite obvious. We choose L as length scale, and our dimensionless length will vary between 0 and 1. It's nice. It's nice when you do numerics. So let's just illustrate this with an example. That's easy, yeah?
Can I ask you, why must it be between 0 and 1?
It doesn't have to be.
Okay.
But we like to know that our variables are kind of of order 1. That's nice. Because, I mean, say in quantum mechanics, you have Planck's constant that is 10 to the minus blah, blah, blah. So you have these ridiculous numbers. So our meter is not appropriate scale for when doing that type of physics, really. We have the speed of light, that is really a large number. So when you're looking at different things, you want to kind of work with a scale that is more like 1, that is suited for the problem. I'll just show you this with an example. It could be, say that sometimes it's really nice maybe to have x between 0 and pi instead. It's more natural. Makes the expressions more easy. If you have, say, or 2 pi, if you have periodic things that has a period of 2 pi, That's a natural length for something that's periodic, for instance. So that's also a side with scaling. There is no absolute rule always. It's a bit of, it's not an art really, but it's something but it's not really mystical either, but not always straightforward, depending on the complexity of the problem, of course. So let's look at the following example. We are in English X. That's heat flow in a stick or a rod, let's call it that. It's a one-dimensional thing. So we consider the following. If I have, we're looking at the boundary value problem now. That means it's a partial differential equation, which you have in, sorry, matte 4. It's the heat equation you're looking for. And we have a stick that is, or a rod that has length L. We assume that the temperature, that's U star of X star T star, be the temperature at time T star at position X star. So here we assume that we have so ice cubes at the end of each of the sticks, so that this temperature there is always 0, and also here we have also 0. We use really Fourier's law to derive the heat equation. Which says that thermal energy will be transported the opposite direction of the temperature increase and flows from warm to cold places. So we have the following equation. Yeah, and then we have this thermal diffusivity, which is the thermal conductivity divided by the specific heat capacity multiplied by the density of the medium. But they call it just D. That's the thermal diffusivity. Like that. And we use then physics. So D is thermal diffusivity. It has dimension meters squared per second. And we have imposed the following boundary conditions, as I just wrote down. And maybe we have given some initial condition. Let's take a concrete one. So it's U0 times the sine of pi times x star divided by L. So you see that the temperature goes from 0 up and then down to 0 again when x star equals L. So now let's try to scale this equation. And we will scale it by a specific technique that is quite nice, which really doesn't take much physical insights. It's called balancing the equation. We scale by, we find the time scale. Let's call it large T, by so-called balancing the equation. Because there is no obvious time scale here, is there? Not at least immediately. We don't see any immediate time scale for this problem. The time scale would be something like, say if I heat one side of it, how long time does it take to significantly heat that this heat has traveled to the other side of the stick, for instance? That would be something that we really don't know what that could be yet. So what we do is sort of balancing the equation. Well, I'll show you how. The length scale is obvious. Let x star equal L times x. That's a parameter we know for a given problem. And let T star equal capital T times dimensionless time, where T is to be determined, is to the one we find isn't necessarily exactly the right time scale, but it's it's not too far away, probably. Also, we need to scale the temperature, because that has Kelvin as a unit. Would there be any natural scale for the temperature from the given problem? Any suggestions? You probably can't see it from the differential equation, because the differential equation is linear. So whatever I scale u star with, it will cancel out, you see. However, if you look at the initial condition, you see that the maximum temperature is u naught. That's when we are in the middle of the road. So that means if I put u star equal to u naught times a dimensionless temperature, that would mean that the dimensionless temperature would be a maximum 1 when x star equals L divided by 2, when dimensionless length is equal to a half. And we know that since the endpoints are kept at 0 temperature, the temperature will sink down to 0 everywhere after a long time. So if we scale this way, we know that u will be between 0 and 1. That's nice. So we're looking for this dimensionless temperature as a function of dimensionless time and position. So if we find this function somehow, then the physical temperature is given by is given by u naught times u, and this u without the star is a function of x and t without the star, and we see that x is x star divided by L. And t star divided by t, that's the t. So finding this dimensionless u gives us the physical solution this way. Okay, so let's try to find the problem, or express the problem in terms of dimensionless numbers. Yeah, so let's consider the... Yeah, first of all, we see that we have or 1 t is 0. Yeah?
Should there be a star in x and t on the right hand of the equal?
Here you mean?
No, both.
Where do you... you need to start here, thanks. Super. I really appreciate it when you see I'm goofing around, so please correct me. That's super duper. But the boundary conditions translate to this, so it's more or less the same as for the physical variables, but instead of L you have 1 because the dimensionless length 1 means physical length L. Okay, so let's see what the differential equation translates into. Here we see that when I take the derivative with respect to t and using the t star, and using the chain rule, I get 1 divided by t as the derivative of the core. So we have that du star dt star equals the second u star translates into what? This u naught will be just a factor. There's just this no star here. Sorry, no star there, of course. No star there. This is the dimensionless temperature. This is this u. So this is a dimensionless number between 1 and 0. So if I want to get back my physical temperature, I multiply this u by the u naught. Now it's 4 minutes left. To obtain u star. Sorry. Okie dokie. So taking the derivative, we get this, and we get du. And then I use the chain rule here. So I get the derivative there, is the t, and dt. So typically when you take the derivative, you divide by the scale. That also makes sense in the unit way, because when I take the derivative of something with respect to time, the new unit is you have to divide by time. So this equals u naught, and then I take the second derivative with respect to x star. So I get L twice after taking the derivative 2 times. Then we have the coefficient d, and then we have this like that. So just use plain rules for derivative. And we see that u naught cancels out here, so the equation doesn't give me really anything. So as I collect the terms on the right-hand side, or multiply up, I get TDL squared like that. So this is the equation on dimensionless form, where this coefficient depends on the time scale. So balancing the equation means putting this equals to 1. So TDL squared equal to 1. It's a dimensionless number because everything here is dimensionless, and this is dimensionless, so this has to be dimensionless, or else it won't be dimensionally correct. And giving time scale, L squared divided by D. So that's how we found the time scale, kind of, by so-called balancing the equation, insisting that the coefficient equals to 1. And also physically, this will be a more or less correct time scale, except that it's like 10 times as small maybe as it should be. If we had scaled the length to go that dimensionless x go between 0 and pi, we'd get the more appropriate time scale here for this example. But we don't bother too much about that. How about the initial condition? That translates to that u of x naught. Remember, the dimensionless one is u naught times the dimensionless thing. So it will only be sine of pi x. So you see that when I replace x by x star divided by L, u by u naught multiplied by the dimensionless temperature, you get the physical temperature. And also the differential equation is now like this. And the boundary conditions are so we see that there are actually no physical constants in the dimensions problem. We need only to solve one case, and then we have all the solutions. For any d, any u naught, any m. So that's a technique of balancing the equation, which I use all the time. When I was working as a reservoir engineer, I always write all my equations on dimensionless form. Of course, everyone does. You should. Because now I know that this x is between 0 and 1. U is something that decreases from 1, essentially. The time, dimensionless time, when it's equals to 1, then the physical time equals this, which is a typical time scale for the problem. Yes, so we'll continue with scaling with a more actually an easier example, except that it includes a couple of forces we have to relate to, and we have to analyze different physical regimes and doing the scaling differently depending on what regime we are studying. As if we had done, say, turbulent flow or laminar flow, we would have scaled different ways probably somehow. Yep. Okay, see you on Wednesday.